Now it turns out that atoms can absorb and emit light, and now we're going to talk about how. And if you understand the quantum hypothesis, the thought that that energy only exists in little packets of certain sizes, then you can understand the process by which atoms absorb and emit light. Now here's how it works. Imagine taking some material and heating it up really hot. For example, you turn on an electric stove. And when you turn it on, it gets hot, and you know what happens. It starts to glow red. It can get hot enough to emit light. What's going on inside the atoms is that because of the heat, electrons are getting kicked up to higher energy levels. And we can draw that like this. We can draw the nucleus of an atom, and then we can draw these concentric circles around it, and we can imagine a little electron here getting kicked up to a higher energy level, so it now exists up here. And sometimes the term used is excited. The electron has been excited to a higher energy state. Now the electron can sit there at the higher energy level for a little while, but at any moment it might fall back to a lower energy level. And we would draw that something like this. Here's these lines representing different energy levels. And if an electron is up here and it falls down to a lower energy level, so it ends up there, what happens is a photon of light is emitted. And so we'll draw the photon commonly like this. It's usually drawn as a little wavy arrow. And the wavy arrow there gives us an idea of it being a photon, because photon is light and light has a wave nature to it. So that's a common symbol for a photon, just a little wavy arrow, and it comes out of the atom as an electron falls down to a lower energy level. So the electron has lost energy, and where has the energy gone? It's gone into this light wave. That photon has been emitted by the atom as a result of that electron dropping down to a lower energy level. And that's where the light comes from when the stove is glowing. The heat is kicking the electrons up to a higher energy level, and as they drop back to a lower energy level, they emit those photons, and that's the red glow of the stove. And it's also common to see a diagram something like this. You can imagine your atom over here. We'll draw another one, and we'll put a few energy levels here. And let's imagine an electron down here, and a photon comes in. And the atom can absorb the photon. Well, that's energy going into the atom. How does the atom hold that energy? Well, that electron gets kicked up to a higher energy level. So these are both very common pictures in the world of quantum physics. This first picture shows an atom absorbing a photon and the electron getting kicked up to a higher energy level. And this second picture shows the electron dropping down to a lower energy level and the atom emitting a photon. Now there's one other thing, and this will hopefully tie it all together. The difference in these energy levels, and you could think of them as the distance represented between these two lines. This line right here is one energy level, and this is another. So the difference between them represents a certain amount of energy. Or these two energy levels right here, the difference between those two energy levels represents how much energy the electron gains when it goes up from the lower one to the higher one, or how much it loses when it goes from the higher to the lower. There's a difference in those energy levels. Different energy levels exist naturally in different atoms. So if you were to actually put numbers on these, in a hydrogen atom, for example, there'd be a certain amount of energy between those two energy levels and a certain amount of energy between those two energy levels. And those numbers would be different for a helium atom or a lithium atom or a carbon atom. Different atoms have different energy levels. And in general, a large drop corresponds to a large amount of energy, and a photon released from a large drop has more energy. So say an electron started way up here and fell all the way down to there. That would be a larger drop, and the photon that was emitted from that drop in energy of the electron would be a higher energy photon. It would literally have more energy. And higher energy photons correspond to higher frequency light waves. Lower energy photons correspond to lower frequency light waves. And the different frequencies of light correspond to the different colors that we see. Just like different frequencies of sound correspond to different notes that we hear, different frequencies of light correspond to different colors that we see if the light is visible. If it's a really high frequency, it might be beyond the frequency of visible light, higher than blue or violet, it would be ultraviolet or even higher. If it were really low frequency light, it would be down below the red, it might be infrared or even lower, down radio waves or lower frequencies. But in general, the different frequencies of light correspond to different colors. And because different atoms naturally have different energy levels, then the light emitted by those atoms naturally comes at certain specific frequencies. So the drop, for example, from one energy level to another, emitting a photon, is going to be is going to emit a photon of one frequency for, say, a carbon atom and another frequency for, say, an oxygen atom. So different atoms emit light at different frequencies. And that brings it back around to the spectrum that we were looking at earlier. If you remember this picture and others like it, this shows the light emitted by two different atoms here. The top row are the frequencies of light emitted by a helium atom, and the bottom row, as you see, by a neon atom. But because the two atoms are different and naturally have different energy levels, they emit different photons, or photons of different frequencies. And in this diagram, the higher frequency blue photons are over here on the left side of the picture, and the lower frequency red photons are over there on the right. And it could be flipped around, it doesn't really matter. It would contain the same information. The point is that different elements emit light at different frequencies, and so each element has this characteristic spectrum that we see, and we looked at that back at the very beginning of this section. And all of this goes to say that these ideas explain this, and this is what makes a scientific theory a good theory. It fits the data. Scientists actually see this, and you can see these colors emitted, and they're different for different elements. And the question comes up, why? Why do we see light emitted differently from helium than from neon, or from hydrogen, or from oxygen, or from anything else? And the reason we see light differently, light emitted differently from different elements, is because of these different energy levels. All of this is explained by these ideas in quantum mechanics. So all this talk about light being a wave and being able to exist at different frequencies and being able to carry different amounts of energy, and about light being able to be absorbed or emitted by an atom, and about electrons existing at different energy levels, all of this fits together nicely and consistently and explains the observed phenomenon. And that's what makes a theory a good theory. It matches the data that we actually see. Measurements that we actually take are consistent with these theoretical ideas.